All right, well, welcome everyone. I am JJ. Let's go ahead and tackle an example problem. In this one, we're saying let's determine the maximum value of our force P that we can apply into the system without causing our 100-pound block to begin sliding up the incline. So it's a basic friction problem. Anytime we're doing these ones, we just want to come in and say, let's draw a free body diagram to start out. I need to solve for P ultimately. So we're saying that box slides up the incline. If we were sliding down, our free body diagram would be different. We'll talk about that at the very end. Box slides up though. Our box is sliding up our incline. Let's make our free body diagram, then we'll come in and analyze it. So I can model that box out just as a rectangle here on some inclined surface. I know I have straight to the right entirely in the x direction a force P. We'll get that in there. I have the weight of my box is coming straight down on here. So 100. And where it hits the ground, I need to get in a normal force and a friction force. So I'll put an N in here. N acts perpendicular to the ground. So if the ground is inclined at 15 degrees from horizontal, our normal force is then 15 degrees from vertical. And then our very last thing we need is a friction force in here. Friction should resist motion. If I'm about to slide up the incline, my friction should be pointing down the incline. I know I'm about to slide. We're checking sliding in here, not tipping. So I'm going to call this FS. That maximum static friction force, because it's not going to be the maximum force P if we're not just about to start sliding. But I know in here this Fs should be mu times our normal force. If it's not Fs, I can't do mu n. Different problem type then. But we're about to slide, so we can call this Fs. It's mu times our normal force. So if I get my normal force, I can get Fs. It's kind of how we're going to go in and tackle this. What are we going to set up in here? I have 1, 2, 3 unknowns in here, P, N, Fs. That means I need 3 equations. One of them I've really written out here. This is one of my 3 equations. Fs is mu times the normal force. We know it's at 15 degrees. So that's one equation, and then it's just equilibrium. I can sum forces in the x for a second one. I can sum forces in the y for my third equation. So let's just set those up. I'm going to start by summing forces in the y direction. If I sum up my forces in the y, I'm going to have, well, my normal force has a y component. I'm coming from vertical on that, so I need to use cosine. So this is n cosine of 15 will give me the y component here. P is only in the x. My Fs has a normal force, so let's get it in here. And my 100 is straight down. Let's get that in there first. Minus 100 from the weight of the box. And then minus the friction force. Minus Fs sine 15. And if we're in equilibrium, we know this should add up and get us to 0. Equals 0. Let's make some substitutions in here. I can say, as I come in and do this, I have N and Fs in here. This gets us that our normal force times the cosine of 15 plus mu times our normal force. Well, mu was given as 0.4. So this shouldn't be plus. This should be minus Fs sine 15, or minus 0.4 n. Mu, 0.4 times our normal force. Sine 15 is going to get us to 100. Equals 100. I've just moved that 100 to the other side. And now I have it down to just n as an unknown. I can solve for my normal force. I will get from that my normal force, n, is equal to 116 pounds. Which isn't an answer, but it's a key calculation for us. With that known, I can come in and say, why don't I sum up forces in the x direction? That'd be my third equation. I can get to 3 unknowns out from that. Also, if I needed it, I know and I can find my friction force now. But let's sum up our forces in the x direction. This is going to get me, well, I have my force P here is entirely in the x. So P, that's the force to slide the box up the incline. I have My normal force has a tiny bit of a x component acting to the left. If my angle comes from vertical, sine opposite would get that x component. I'm going to subtract that off. Minus n 1/16 times the sine of 15. And then finally, my friction also points to the left, which let's make that mu n substitution as we set this up. Minus our friction, minus 0.4 times n, 1/16. Mu times our normal force is the friction force, times, I'm at an angle here, I want the cosine of 15. Cosine 15 is going to get us to 0. If P is my only unknown in this, I can solve this and get that my force to move the box up the incline would be 74.8 pounds. And that would be my final answer in our problem here. If we are asked for what's the range of values of P for equilibrium, this would be half of our answer. This would be 1 bound. I would also be able to say, though, there's some force that would pull P, or some force P that would be moving it down the incline. I would just set that up and expect a negative value in here. But I could sum force in the x and the y again, except my key difference in my free body diagram is if I'm sliding down that incline, my friction force acts up the incline. Changes that around, which is going to change all of my numbers around then and get to a different end result for everything. But really, it's a simple step. If we can get to here, just redo the free body diagram. You can get the range of values for equilibrium. But hopefully this is a useful video. If it was, hit those like and subscribe buttons. Stick around. Let's get you in there with JJ.